understandably don't like earthquakes, but you know what? Living in California, earthquakes are kind of a frequency around here. But as long as you have an earthquake that's like somewhere between like a 2.0 and a 4.0, they rock stuff around. They don't really cause that much damage. And I don't know. Every once in a while, one waking up at 4 in the morning, it's a start. It startles you, but afterwards you're like, oh, that was pretty cool. And then yeah, slinky toys are pretty fun in my opinion, unless you get them tangled. So if you don't see the theme yet, all these have one thing in common, and that is that they all deal with a different type of wave. So today we're going to be learning about waves. All right, let me say the disclaimers. So again, please don't share any personal information during class. Your participation is going to be required as always, and these sessions are still being recorded for learning purposes. All right. So for our schedule, today is Monday. We're starting a new unit with a brand new week here. So yeah, the entire unit is going to be dealing with waves. So waves can take many forms in like many different types of physical like types of matter. We can have waves in the ocean, we can have sound waves, but they all have the same thing in common, which is kind of like their geometry or their math. So that's probably what we're going to be focusing on. All right. Specifically today, we're covering like the basics. We're going to define mechanical and electromagnetic waves. We're going to define types of mechanical waves and provide examples, and identify different aspects of waves called the crest, the trough, the amplitude, and the wavelength of the wave itself. All right. Go ahead, and we should have the links. Yeah, the links are down towards the bottom of the chat. If you haven't already, please take out your notes and raise your hand when you're ready to move on.
Quick announcement here. I am actually going on maternity leave on Monday, May 24th, and I will not be returning for the remainder of trimester 3. So that means in 2 weeks, I am leaving officially for the rest of trimester 3. So just to make sure, sorry, I'm going to miss y'all. Hopefully if you're graduating, hopefully I'll be able to make it to graduation though, but we'll see, because that's going to be really close to birth time. So we'll see. But just to help you guys out, I will be having office hours every single day for the next 2 weeks at 2 p.m. to help out specifically with projects. Thank you, Lena. So I really, really recommend that all of your projects are submitted before I leave. Unit 1, the airplane project, Unit 2, the drop project, and Unit 3, the roller coaster project. Again, 2 weeks, try to get them all caught up, because once I leave, I don't know what the substitute situation is going to be. So I don't know exactly like how much support you'll be able to get after I leave. So I really recommend, if you want as much support as possible, try to get it done now. Regardless of if you're enrolled as my student or Mr. Bangles, everybody's been invited to those office hours. So if you're missing any projects, come to those office hours. Please work on those projects, get them done before I leave, just so that you know that you're all squared away before I leave. Thank you, Lexi. Additionally, just so you know, the Unit 4 project is going to be replaced with an exam, just to make grading easier for the substitute teachers. The exam is still really important, and in fact, we actually grade harder on exams than projects, because projects are graded on a 5 through 10 scale, whereas exams are graded on a normal scale. But it will be a little bit faster for substitutes to grade them. Again, I don't know what the sub situation is going to be, so I'm just trying to plan ahead to make it easier for them, to make sure that they're prepared to support you. You will still have a normal final exam. Final exam is unchanged, but just again, so you know, Unit 4 project is being replaced with an exam. Okay. So again, just really, really important reminder. Try to get your projects done before I leave for the rest of the trimester. Okay, so 2 weeks to get those projects all completed and good to go. Okay, so let's go ahead and start our brainstorm here. I'm going to go ahead and show you a stadium wave, and I want you to go ahead and tell me, what do you notice each person is doing in the stadium wave? And then what do you notice it ends up like looking like? All right, so we're going to go ahead and go over this. Let me go ahead and share this with y'all up on the whiteboard. You can find my video. Here it is. All right, I'm going to share this. All right, here we go. Gonna go ahead and share this with you up on the board. I have no idea what the score here is. Tell me in the chat though, what did you notice each person had to do in order to make the stadium wave happen? Alexia, I do not actually know what I'm having. It's going to be a surprise. My daughter, my first kid, was also a surprise. So I feel like that's more fun. So I'll let you know once I have the baby. So what did each person have to do in order to make this stadium wave happen? Tell me in the chat. I see Joseph H. Let's get some more participation. Cody, Kamal, Alicia. Thank you. I see Lexi in the chat. Tell me what you see happening, Caden, Alan. Again, I can probably go back to a specific spot. So like right here, what do you notice these people are doing? What do you notice these people are doing to make the stadium wave happen? Right here. I know, it's a little bit laggy. That's okay. I can always share this with you as a link as well in just a moment. Chantal, Seraphim, Kalina, Shayna, Itati, Carlos, Benjamin, Jayland, Alan, Caden, tell me in the chat, what do you notice happens to make a stadium wave? What does each person have to do to make a stadium wave? You already have some classmates that answered, so it's okay for you to have the same answer. Just as long as you're participating, that helps to reinforce your own learning. Yeah, I already played it, Carlos. Can you not see it up on the board though? Yeah, so they have to stand and they have to sit back down, and particularly they have to stand and sit at the right time, right? So like this section stood and sat, and then the next section stood and sat, and so on and so forth until it made it all the way around to here. Now, what I want you to think about though, here, I'll share this with you for anyone that was having a hard time seeing it. Here's that link, okay, if you want to take a look at it later. But what I want you to think about here is that, were the people actually moving? Okay, so was anyone actually moving away from their seat? We saw the wave go around the stadium, but did anyone have to actually leave their seat to make that wave happen, to make that wave go around the stadium? Did anyone have to run around the stadium? No. So this is important to understand that all they had to do was stand up and sit down, but they stayed in their seat. And this is going to be important when we talk about mechanical waves, where particles kind of stay in their seat. All right. They don't actually move with the wave. It's just that by the way that that particle moves can transfer the energy without them leaving their seat. In the same way in a stadium wave, nobody has to leave their seat. All right. Let's go ahead and take a look here. So all waves, regardless of if they're mechanical or electromagnetic, we're going to talk about that in just a moment, all waves transfer energy in some form or another. Okay, so mechanical waves require what is called a medium. That means that they require some form of matter. That could be a solid, a liquid, or a gas, like water, air, earth. What else? So all of those things are a slinky, right, requires metal. So all of those things there are physical substances. So when you think about mechanical waves, you should think about something that is physical. Okay, just like mechanical, think about how like an actual mechanic physically works on a machine. Smiley faces, emojis in the chat if that makes sense. So all waves transfer energy, but mechanical waves specifically do it with a physical substance, with a medium, with matter. Okay. Now, again, that energy just gets passed particle to particle, okay? Just like that energy in our stadium wave got passed from person to person, it's the same thing with mechanical waves. It gets passed from particle to particle. The particles never actually have to leave their seat. They're just kind of passing on the energy, just like the people in the stadium wave. Now, again, that makes sense because particles mean that there's a physical substance. Again, this idea that mechanical waves have to have a physical substance. Now, on the other hand, electromagnetic waves, okay, actually do not require a medium, which is really important because our sun, the thing that keeps us warm and alive, emits electromagnetic waves. And if it required a medium, it would not be able to travel through outer space because there is no particles in outer space. Space is a vacuum, which means there's no water, air, or solids between us and the sun. All right, so again, electromagnetic waves don't require a medium. Go ahead and give me a green check, orange X if that makes sense. The difference between mechanical, you need something physical. Electromagnetic, you don't need something physical to move them. Okay, excellent. All right, so that means that electromagnetic waves can travel through a vacuum. such as outer space. They don't need any matter. And an example here is light waves. So light waves are not physical substances. Light waves can travel without needing matter. They don't need solids, liquids, or gases in order to travel. Again, super important, because if that was not true, then light would never reach the Earth and we would not be alive. So electromagnetic waves, really important that they can travel through outer space to reach you and I. This is number 2. Go ahead and fill in the blank. Regardless of if you're mechanical or electromagnetic, you are still transferring energy. Number 2 is energy. 20 seconds to fill in the blank and raise your hand. Okay, so mechanical waves, again, the ones that are physical, like a mechanic needs a physical substance to work on. Mechanical waves, again, do not actually move their matter, their physical substances, from its location. So this is just like our stadium wave. So the medium's particles can go up and down, they can go back and forth, they can even go in circles, but they don't actually travel with the wave. All right, just like in our stadium wave, nobody actually had to run around the stadium. All they had to do was stand up and down, but nobody moved away from their seats. And this is also true with all physical mechanical waves. Nobody has to leave their seats. The particles stay in their spot, kind of going up and down, side to side in a circle, but they're not actually leaving their seats. They're just passing on the energy. Again, they transfer energy, electromagnetic waves transfer energy, but mechanical waves specifically do it by taking the energy from one particle and passing it on to the next particle, kind of like a game of telephone, okay? Go ahead, give me a smiley, medium, sad face if that's beginning to make sense. Again, mechanical waves are physical waves, physically need matter, but again, the particles themselves are not moving. They are staying in their spots just like people in a stadium wave. They are not leaving their spot to transfer that energy. They're just passing it on like a game of telephone. Great. All right, let's make sure that this makes sense. This is number 3. Go ahead and fill in the blank with the word travel, only the word travel. 20 seconds to raise your hands. And we talked about 2 types of wave, mechanical versus electromagnetic. The rest of the lesson, we're going to be focusing on mechanical waves.
Let's go ahead and practice this using some matching. So we have 2 terms with multiple definitions. So our 2 terms are either going to be mechanical waves or electromagnetic waves. And then we have multiple definitions that could apply to either one. So one is they do not require a medium. They're also called light waves. Another one would require a medium. Another one can move through a vacuum like space. And one of them is where a wave is passed from particle to particle. All right, our whiteboard tools are on. Let's use our thin lines on the whiteboard tools to match those up. All right, that's a little bit better, guys. So let's go ahead and review this. So we did have a couple mistakes, one of them I saw was we were thinking that electromagnetic waves had a wave that was passed from particle to particle. Remember that the only particles that that we're dealing with, right? Particles are physical, so that would be mechanical. So mechanical waves require a medium to travel through, like air, water, or earth, and that's why we can say they're passed from particle to particle, because like think of like particles of air or particles of water, right? Particles are physical. All right, but then with electromagnetic waves, they do not require a medium because they can go through space, which is literally a vacuum of nothing. And they're also called light waves. We'll learn more about that with like the different wavelengths. And they can also move through a vacuum like space, which I kind of already said. So a vacuum is like the term we give to the absence of a medium, if anyone's curious. So go ahead and raise your hands for number 4. All right, so learning a bit about types of mechanical waves. So we know that a mechanical wave has to deal with something that's physical. All right, just remember that in a mechanical wave, the energy travels, but the particles stay in the same seat, right? Just like the stadium wave. So here we have 3 types of mechanical waves. We have the transverse, where particles move perpendicular to the direction of energy. We have longitudinal, where particles move parallel to the energy, and surface, where particles move in circles. So here we have illustrations for what parallel and perpendicular mean again. So perpendicular, right? The transverse waves would be having particles moving up and down along the wave. Longitudinal waves, the particles are actually moving side to side along that same direction as the energy. All right, we're showing this kind of like with a spring. And then with a surface wave, this is kind of like, I think, how ocean waves work. The particles are actually moving in circles, and each circle kind of works like a gear and like a clock leading to the next circle that pushes the particles along. So, but we'll look into these in more detail in the following slides. But just for now, give me a happy face, medium face, or sad face if this is starting to make sense. Good to see, good to see. All right, just wanted to make sure I didn't botch my explanation too much. So let's move on from there.
All right, so let's go ahead and talk a little bit more in depth about each of these types of waves. So longitudinal waves, the way I remember this is longitudinal has the word long in it. And so what I think is like the particles move along with the longitudinal waves. Smiley faces, emojis in the chat if that makes sense. All right, so they move along with the wave. So in other words, they move in the same sort of direction, back and forth along with the energy, okay? So particles are going to move parallel to the direction of the wave's energy. Again, the actual particles don't move far from their seats, but they are going to move back and forth along the same direction as the wave's energy. So if the wave is going left to right, then the particles will move back and forth left and right, okay? Or if it's going up and down, the particles will move up and down along with the same direction of the energy. Examples here are sound waves and springs. All right, assuming you push a spring, all right, you will see that the spring or the sound, the particles are all kind of just moving in their spots. So let's go ahead and take a look at an actual GIF of this, a GIF of this, because I feel like that's always easier to actually visualize. So I'm going to go ahead and share this with you. All right, go ahead, give me a smiley face in the chat if you can see my screen here. You can see my screen up here. All right, awesome. All right, so what I want you to take a look at is take a look at one of the red dots. All right, there are 3 red dots up here. And tell me, how are those red dots moving? Are they going up and down, left and right? Tell me in the chat, how are those red dots moving? Are they going all the way to the right, all the way to the left? What do you see those red dots doing? They are moving, right? They're not moving a ton though, right? They're not going from one edge to another edge. Right, but they are moving, and which way are they moving? Yeah, they're kind of going back and forth left and right. So what we can see is that the energy starts over here on the left and is getting transferred over here to the right. However, again, nobody is leaving their so-called seats. Those red particles are still kind of staying in their seat. They're just kind of pushing back and forth to transfer the energy. Go ahead and give me a smiley or an emoji in the chat if that makes sense. Again, the actual particles of the medium do not leave their seat. They pass along the message and then they stay in their seat. They pass along the message and then they stay in their seat. Again, here though, they're moving parallel. So since the energy is going left to right, the particles are moving back and forward, left and right. Okay, awesome. All right, let's go ahead and then take a look here at our next one. Moving back over here. Okay, so our next one here is going to be transverse waves. So transverse waves, the particles are going to move perpendicular, all right, to the direction of the wave's energy. An example here would be a guitar string or like a jump rope. So in this case, when you wiggle a rope, all right, the particles are going to move up and down while the energy moves to the side. So previously we saw longitudinal, energy is moving to the side, particles also move side to side. Here, though, the energy is going to move to the side, but the particles are going to actually move up and down as they pass on that message. Again, though, nobody leaves their seats. Let's go ahead and show this one to us up on the whiteboard. Again, we're going to take a look at the red particles and see what's happening with the red particles. Let me share this with you. And here we go. All right. So what I want you to tell me here is, again, take a look at one of the red particles and tell me, follow that red particle and tell me, what do you notice that red particle is doing? Take a look at just one red particle and tell me, what do you notice that red particle is doing? How is that red particle moving? Thank you. I see Cody in the chat. Let's get some more participation. Carlos, Mallory, Kaden, Alicia, Kamal, Lexi, Jalen, Benjamin, Itati, Shayna. Yes, thank you, Lexi. Thank you, Mallory. Yeah, exactly. So again, we can see our energy is starting over here and it's moving to the right, but the individual particles are not moving away from their seat. They're going up and down, they're sending on the message, but nobody leaves their seat. Otherwise, every single time you kind of used a jump rope, the jump rope would run away from your hands, which would be very silly, right? So at no point is the physical substance leaving your hands, right? It's just transferring the energy by like a game of telephone. So again, they move up and down in their seats just like a stadium wave, but nobody actually leaves their seats. Again, you should be able to, at this point, recognize a pattern going on here. Okay, last type here is going to be surface waves. So surface waves, the particles move in a circular motion. What's actually happening is surface waves are a combination of the two types of directions, parallel and perpendicular. And this happens at a surface where two different mediums touch. So air meets water in an ocean wave. So that's a gas meeting a liquid, two different mediums. Or for example, in an earthquake, a seismic wave, air meets the earth. So a gas meets a solid. So this is where surface waves happen between two surfaces. Now, the particles near the surface are going to make different size circles than the particles away from the surface. So let's go ahead and take a look here at the GIF of this. If I can find it, where'd it go? Here it is. All right, I'm going to go ahead and share this one with you. This time, you're going to take a look at the orange particles. All right, so this time, take a look at one of the orange particles and tell me, what are the orange particles doing? Again, we can see that energy overall going from left to right, but the individual particles are doing what? The individual particles are doing what? Please respond quickly. We still have a lot to get through, everyone, so the faster you respond, the less we have to stay after class. Please respond quickly. What are the orange particles doing? Thank you, Chantal. Thank you, Edwin. Yeah, again, they're kind of spinning, rotating. They're moving in a circle, exactly, as I mentioned. Now, you will notice that the circle on top, is that bigger or smaller than the circle on the bottom? The circle on top, is that bigger or smaller than the circle on the bottom? Thank you, Joseph. Let's get some more observations in the chat. The circle on the top, is it bigger or smaller? Thank you, Mallory. Yeah, it's definitely bigger. Exactly, Shayna. All right, so that's important to understand, because what I want you to think about is if you go to the ocean, all right, and you have, all right, if you have a huge wave coming towards you, all right, what do you think you should do? Should you stand up as the wave hits you, or should you duck under the water? What would be a better decision? Tell me in the chat. If you've ever experienced this at the beach, what hurts less, to stand up as the wave comes towards you, or to duck under the water as the wave comes towards you? Yeah, it's actually a lot better to duck. All right, again, we see this right here, that the higher up you are, the bigger those circles are, and the more energy these surface waves have, the more they're going to hurt. All right, the lower down you go, though, you'll see that those surface waves really quickly become much smaller. And so those surface waves below the surface have much less energy. And so it doesn't hurt as much when that wave comes towards you. So just as a helpful trick, if you go to the beach, if you have a big wave coming towards you, go under the wave instead of standing up into the wave. Okay, let's go ahead and match these up.
Okay, so practicing what these mean while looking at the actual diagrams, let's use our thin non-red lines to match these up. We have our longitudinal, surface, and transverse waves. Please match them up with the descriptions and the pictures. All right. I believe the explanations do go with the picture, so you don't have to match those separately. They are together. Looking good. And then this is going to be number 5 in our notes. So yeah, longitudinal waves, they move parallel, kind of like if we push and pull along this spring. And then surface waves, again, is that circular motion. And then transverse waves are when it's literally going up and down to make the wave happen, right? Just like the stadium wave. All right, so let's raise our hands for number 5. All right, so learning points on a wave. So there's different parts of the wave that have names. So the crest is a point on medium with max upward displacement from equilibrium. So the crest is kind of like the very tippy top of the wave and the very low point of the, okay, excuse me. No, that's the opposite. Yeah, crests are just the very tops of the wave. It's like the top of a mountain. And then the trough is actually the opposite of the crest. It's the very, very bottom of the wave. So trough is the lowest point, crest is the highest point. All right. Sorry if that didn't make sense for a second there. Just give me some faces to see how we feel about this. Again, pretty simple, as long as I explained it correctly. All right, cool. So let's move on from there. Remembering, right, trough is the lowest point, crest is the highest point.
Awesome. Okay, so that's really important to understand. Crest and trough are points on the wave. Now we're going to go ahead and talk about actual measurements. So amplitude and wavelength are two measurements on a wave, and these are different because they're not single points. They're actual lengths or distances. So the amplitude is going to be the overall height of the hill from the rest, the equilibrium, the middle point, either to the top of the crest or to the bottom of the trough. Right, so you could say rest to crest or rest to trough. That is the height of the actual wave, and it's mirror images. So, right, so the height of the top part of the wave versus the height of the bottom part of the wave are identical to each other. Smiley faces emojis if that makes sense. All right, so the crest and the trough are the actual points. The amplitude is then the height of those points. The height of those points, the overall distance. Okay, this is important to understand. The greater amplitude there is, the more energy there is. So for example, when you see sound waves on like videos and stuff, you'll see the sound wave get really big as people are yelling, and that is, or singing really loudly, and that is showing that it has a lot more energy. Same thing with the ocean wave. Big waves hurt more because they have more energy, right? Their height is much bigger. Now the wavelength is the length of one wave. All right, so that should be really easy. You can see the word length of a wave. So again, this is not the same as a single point. It's an actual distance overall. So it's going to be the length of one wave cycle. And so this means it's from one identical point to another identical point. So most of the time we measure it from crest to crest, which are two identical points. But you could also measure it from trough to trough, another two identical points. Or you can measure it from 2 points across the equilibrium that are the same. So in this case, we're going down across the equilibrium, and we're going down across the equilibrium again over here, right? You wouldn't measure to this point. This point's actually going up across the equilibrium, okay? So it's from one identical point to another identical point. All of these would end up being the same wavelength, all right? So as long as it's from one point to its identical point, that will be a single wave cycle. That would be the length of one wave. So wavelength, length of a wave, okay? Let's go ahead and make sure that that makes sense. Again, remember, crest and trough are points. Amplitude and wavelength are actual lengths or distances. Here we go. Let's go ahead and match these up, and I'll let Mr. Bingle take over.
All right, so using our thin lines again, let's match up the different parts of the wave we just learned about. Let's use our whiteboard tools. We have amplitude, crest, trough, wavelength. Remember, two of these are points on a wave, and then the other two terms are the measurements of the wave. So let's try to keep those straight in our minds. So so let's just start with the crest. So the crest is the highest point on a wave, trough is the lowest point of the wave. Right? Wavelength, right? That's the length from crest to crest. So that's kind of like the longitudinal measurement that we're doing. Amplitude is kind of like the height of the wave. It's from crest to trough, trough to crest.
Rest to crest, like the equilibrium.
Okay, my mistake. All right, rest to crest, rest to trough. Right, let's be raising our hands.
So here's what's going to happen. You're going to identify the amplitude, crest, trough, and wavelength for the wave in the following diagram. Now, again, I do want to make a point here that C and D are actual points. All right, so C is the point. All right, and D is a point, okay? Whereas the arrows here are showing lengths or distances, all right? So you can see here A is a length and B is a length, all right? So this one's an actual length from side to side. This one is an actual length up and down, Okay, so again, you should be able to use your definitions from question number 6 to match up A, B, C, and D. If you want to double check any answers, go ahead and let us know in the Q&A box, but you do need to make sure you try it before you check your answers. Go ahead, I'm going to clear out your hands and raise your hands for number 7 once you have number 7 completed. Again, use your definitions from question 6. Again, C and D are points, A and B are actual lengths. So that should help you out. Go, go, go. I'll give you another 20 seconds.
All right, great job today, guys. We covered the basics about waves. So we defined mechanical and electromagnetic waves. We learned about all the different types of mechanical waves, and we identified the different parts of waves, such as the crest, trough, amplitude, and wavelength. All right, great job, everyone. Just go ahead and, if you haven't already, submit your notes. And if you have no questions, go ahead, feel free to leave the class, and have a great day, everyone. We will see you guys tomorrow.